On March 2011, the city of Kesennuma was one of the many cities in Japan that was tragically affected by a 9.0 magnitude earthquake. The earthquake generated a tsunami that destroyed the city. This project encompasses designs to prepare for the next projected tsunami, which will be predicted to occur within the next 1,000 years. The various aspects of this project will include structural, geotechnical, transportation, hydraulics, and construction in the overall design.
An evacuation plan was designed to direct the residents of Kesennuma to higher ground and out of the tsunami boundary. In order to decrease confusion and panic, 4 areas within the town are going to be designated as assembly areas where residents can gather. These assembly areas will include evacuation plans similar to Figure 1 to provide visual public awareness. These plans will also show locations of the 3 towers/parking structures that are located on a higher elevation and outside the hazard area. ISO approved international signage for tsunami hazard zones, evacuation areas, and evacuation buildings will be used. These signs will indicate the tsunami zone and provide guidance. The layout of the roads in the town was redesigned in order to suit the residents' needs. The commercial area of the town was relocated to the fishing port area, while the residential area was relocated behind the commercial area for better protection of the residents. The placement of a channel will cross 4 minor roads, which will require 4 bridges. The redesign of the roads include a pedestrian walkway, a bike path, and 2-lane roads, 1 in each direction.
The main focus of the hydraulic engineer was to utilize as much of the energy from the incoming water from the tsunami by slowing down, which was then directed to the channel. The open channel will be placed at the mouth of the bay and end to connect to a river where the flow of water will be redirected to the ocean. At the opposing side, a jetty will be placed to help direct the water into the channel. Manning's equation was used to determine the dimension of the channel as shown by the figure on the slide. The channel will have a base of 140 feet and depth of 33 feet. Aside from directing the water, it was also important to consider ways to help dissipate the energy from the waves to decrease the velocity. The sides of the channel will be lined with mangroves, which are deep-rooted trees. The purpose of the mangroves is to slow down the flow of water as well as prevent some of the debris from moving further into the town. The base of the channel will be lined with riprap, which is composed of stone, cobbles, and boulders.
As part of the solution to reconstruct Kesennuma, and in order to make it a city that can withstand a tsunami similar to the one that occurred in 2011, our team developed the idea of constructing elevated safety towers where people can evacuate to in the event of a tsunami. These towers are elevated by 32 feet. The first 3 levels will perform as a parking garage, and the 4th level will be the evacuation tower. These structures will be constructed out of concrete floors over concrete beams and columns. As part of the reconstruction, our team also designed several bridges to provide easy access for the residents to reach the evacuation towers and also to allow for a channel to redirect the water coming in from the tsunami wave. The bridges were designed as steel truss bridges over concrete abutments and concrete columns with a span of 172 feet.
The geotechnical process began with the soil classification of Kesennuma obtained from SPT data. The soil ranges from fine sand to medium fine sand. Kesennuma is highly susceptible to liquefaction. Approximately 40% of the soil profile will liquefy. Liquefaction occurs when the soil becomes saturated due to earthquake shaking or rapid loading. This decreases the strength and stiffness of the soil, potentially causing tremendous failure. The construction of the drilled shafts embedded into the bedrock will be the best solution to obtain a higher load capacity, preventing failure of the bridges and the parking structures during an earthquake or a tsunami. There will be a total of 32 drilled shafts. Each parking structure will require 36 drilled shafts, and each of the bridges will require 6 drilled shafts. The shafts will have a diameter of 1 foot and will be a length of 69.9 feet.
The team's design is composed of 3 parking structures, 4 bridges, 1 channel, and roadwork. The construction engineer had to schedule each individual project and combine them as a whole. The total time of the schedule is approximately 18 months to complete all the projects simultaneously. These slides show the Gantt chart of the schedule. Another task of the construction engineer was to create a cost estimate for the project. The slide here shows the summary of the projects and the total cost of the project, which turned out to be approximately $70 million. This concludes our video. Thank you.